So in the strategy that we outlined in the last video, the first thing was to find the energy terms for electron-electron repulsion between the two electrons, because it's a D2 state, in the free vanadium ion, which has spherical symmetry. Because this is only one atom now, we have to go over the term symbols for atoms. And I think you have learned this in PChem, hopefully, but I'm going to review it here as well. So for atoms, you have the spin multiplicity, 2s plus 1, that you write as a superscript, and then you have L. And this is based upon the subshell that you're in, right? So L equals 0 gives you an S, L equals 1, P, etc. Okay. So in electronic states, the orbital magnetic moments, M sub L, and spin magnetic moments, M sub S, interact to give a certain energy for a given electron configuration. Except for fully filled configurations, so that's going to be like D10, no one microstate fully describes the configuration's energy. And what we're going to use is something called the Russell-Saunders scheme that allows us to assess the energies of individual microstates. Basically what this tells you is that you can treat the individual M sub L's and M sub S's of each electron individually and then add them up together to coupling them. This is Russell-Saunders scheme. Now, this is an assumption, this is simplification, this is not totally valid. And it turns out this is a good approximation for first and second row transition metals. There's this pesky idea of spin orbit coupling that occurs when you get down, that's especially prominent when you get down to the third row transition metals and any of the F elements. And this gives rise to more quantum numbers. So there's additional quantum numbers and more states. Basically, things just get more complicated. You get more states, which eventually gives rise, typically to more peaks in your spectrum. But we're not going to worry about that now. We're going to assume that you can just add the electrons together. Like if you have the microstate of one electron and another electron in your D2 configuration, the total configuration is going to be just the sum of those two. And they're not going to interact strangely. All right, that's not actually totally valid, okay? Because of spin orbit coupling. Spin orbit coupling, remember, says that electrons can couple with one another and further split the electron states. Okay, so let's go over this Russell-Saunders business. We are used to learning about quantum numbers for single electrons. That's what you and I are all comfortable with and what you talk about in general chemistry. Those get lowercase numbers, right? Like lowercase letters, lowercase m sub l, lowercase m sub s. Good. Russell-Saunders, like I said, says we can add up these quantum numbers for multi-electron configurations. That's the assumption that Russell-Saunders made. And we're going to use capital letters here for these multi-electron configurations. Capital L, that gives the total orbital angular momentum of an atomic state. That's equal to the maximum value of m sub l. Let me just pause here to tell you, there's a lot of nomenclature here. It gets pretty complicated. That's okay. The best thing, is to work through an example, and that's what we're going to do. And these slides, you can kind of use as a reference to go back to later as we work through the example. And we'll do that as well in these lectures, okay? But capital L, we're using capital values for these multiple electron states. And L gives the total number, capital L, gives the total number, total orbital angular momentum of an atomic state. That is equal to the maximum value of m sub L possible, capital M sub L. Capital M sub L is the total orbital angular momentum of a microstate. So capital M sub L is just adding up the sum of all the single electron M sub L's, okay? That's what Russell-Saunders coupling is. And capital M sub L value has associated values, L values that can range from negative L to L, okay? Positive L, integer values. Same exact thing with S, okay? Capital S, it's the total spin angular momentum of an atomic state. It's equal to the maximum value of capital M sub S for a given L state. All right, and capital M sub S is the total spin angular momentum of a microstate. Again, it's a summation of all the M sub S's, the lowercase M sub S's. And this can vary from negative S to positive S, okay? We'll go through this and it'll be more clear with an example. And so I think we should probably stop. Well, let's keep going. All right, vanadium 3+ has a valence electron configuration, of course, of argon and then 3d2. That's what we care about. So this is n equals 3 because we're in a 3d. L equals 2, subshell orbital of a d orbital, so that gives you 2. Remember, S is L equals 0, P is L equals 1, D is L equals 2. M sub L, it's a d orbital, so it can go from negative L to positive L, so it can go from -2, -1, 0, 1, and 2. And M sub S, of course, can be -1/2 plus 1/2. These are lowercase quantum numbers I've used, single electron. ML and MS are going to interact to give microstates of different energy. So now we can start looking at, okay, what are our M sub Ls? Our M sub Ls, here's one microstate. Both spin up. One in the 1 subshell with an M sub L of 1. One spin up within the subshell of ML equals 2. And so you sum up these to get capital ML. Capital ML is going to be 1 plus 2, right? Just these two. That means capital ML is going to be equals 3. And both these are spin up. It means each one has a lowercase ms of 1/2. And so a 1/2 plus 1/2 equals 1. That's going to be a capital M sub S. We're going to use a shorthand in order to just simplify this. And we're going to call it 2 plus, 1 plus in parentheses. And what this means is your M sub L, lowercase, is going to be there. You have 1 electron in the 2 subshell, and it's plus. Plus means spin up. Minus means spin down. Okay, and then you have another one, 1 in the 1 subshell, and it's spin up plus, so you put that one. Okay. So what we're going to do in the next video is we're going to derive all 45 microstates. We know there's 45 from that factorial formula that we went over.